Okay. 9, what's going on here? A well-insulated copper can of mass 0.153 kilograms contains some ice and water. The total is 0.24. Alright. So you've got your copper can and its mass is 0.153 kilograms. And you've got in here some water and some ice, and its mass is 0.24 kilograms. The can, water and ice are in thermal equilibrium. So what temperature are all three of them? What is the only temperature all three could be at if they're all at the same temperature? The water, the ice and the can. You're thinking too hard about it. Think less, talk more. What temperature? I know you know this.
0.
There we go. Yeah. 0. Ice can be at 0, water can be at 0. And of course copper can be at lots of temperatures. But it has to be the same as these two. It has to be 0. 0 is the only temperature water and ice can be at together. Because if you're more than 0, you definitely don't have ice. And if you're less than 0, you definitely don't have water. So 0 is the only one that can both be at the same temperature. Okay. Okay, a brass weight is stuck inside of mass 0.5 kilograms. Yeah, you heat the half a kilogram in boiling water and then you quickly put it into the water and ice. So this is at 100 Celsius when it goes in. And then when you mix everything down, it reaches a final temperature of 10.3 Celsius.
What is 0.5?
That's a little bit of a brass weight that they threw into the ice water. And the brass was heated up to 100 Celsius. So the question is, what was the mass of the water? Okay. If we think about this carefully, we can make the equation. So, first thing to get straight in our head, how many masses are there? How many items are there to consider here? I would say 4. What are the 4? Copper is the first one. Water is the second one. Ice is the third one. And brass is the fourth one. Okay. So let's start with the copper. What temperature was the copper at in the beginning? 0. And at the end? Oh no, this copper. Everything became 10.3 at the end when everything was mixed together. Okay. So, did the copper gain or lose energy? Gained. So the formula is M C delta T. There we go. Right, that's the copper done. That's how much energy the copper gained. Right, the liquid water. Did it gain or lose energy? Gained. So the formula is M. Now here's the problem. We don't know how much water we have. We only know how much water and ice we have. Yeah? So what I'll do is I'll call the water X. So if the water is X, then how much ice do I have? It'll be 0.24 minus X, because 0.24 is the total. So that's M C delta theta, 10.3. Okay. Then onto the ice. The ice gained energy. The ice did two things. First it melted, so that's M L, which is 343,000. Then after the ice melted, it became water and heated up. I'm running out of space here. Plus M C delta theta. Okay, so that's how much was gained. Now, how much was lost? Well, the brass lost energy. Okay, it was a 0.5 kilogram brass that had a temperature of 100, but then its temperature dropped to 10.3. So MC, I have to put the C in, MC delta theta. Okay. Now, you basically say the energy lost by the brass equals the energy gained by everything else. So the brass loses energy, and the copper, the ice, and the water, they all gain energy, and the amount that they gain has to equal the amount that the brass lost. So it's 5 marks. But really, it's just solving one linear equation. Now, it's a very messy equation, so you're going to have to say that this equals this. So let's clean it up. So we'll multiply that out first. 0.153 times 385 times 10.3. Do I have any other constants to add to it? So any other constants? No. Okay, so I'll have 606.7215 plus 10.3 times 41880, so that's 43054, 43054x plus, now look, these two guys can be put together because there's this in common to both. So you could actually put this together as 343000 plus 4180 times 10.3. So that's 386054 times 0.24 minus x equals 0.5 times 385 times 100 minus 10.3 equals 17267.25. 17267.25. Yeah? Mistake, please tell me now rather than later.
4180 times 10.3 plus 343.
4180, where's that?
The last two.
4180, oh yeah. Yeah, so what I did was I multiplied these together and added it to this. It's not 386054?
Minus 377.
343000 plus 4180 times 10.3, 386054. Okay, good. Right. Well, actually, since you have the calculator handy, Matt, could you just multiply this 386054 by the 0.24? And Siba, could you take this number and then minus this number, please? Yeah.
92652.96.
One seven zero two zero point five two eight five.
17020
.5285.
5285. Okay. So now, could you keep that number on your calculator and then minus this? Minus this number now. And Matt, could you do this number minus this number, please?
Minus 75632.4315.
Yeah.
Minus 343000.
So you can all see there's only one thing left to do. So if you can type this in and we are done. 0.2205. So if I do three significant figures, it'll be 221 kilograms is the final answer. It'd be wonderful if that was the answer in the marking scheme. It would be delightful. Oh, wonderful.
What's the 0.223?
223! I think our answer is more accurate. 221. Because we kept all the decimal places throughout, didn't we? It's a bit of a pain, that one, but you realise it's really just a maths problem. You have this ugly linear equation to solve. How many marks, when you're ready, Siva, I'm just wondering how many marks they gave you for writing down the equation at the beginning?
Doesn't say the marks.
Oh, doesn't say for the steps? Yeah, go ahead. Can I close this? I mean, well, go on to the next one. A10. Let's see. Save.